All right, guys, this is going to be a quick lesson on electric current and potential difference. This is your introduction to electricity, and yeah, away we go. Like I said, electric current. So, first of all, when we look at a circuit, and I'm not going to test you guys much on circuit symbols, just easy ones that you can look up, but we can think of current as traveling in one of two ways. You can think of it in terms of electrons traveling from the negative terminal to the positive terminal. Now, let me just show you a picture of that. So this right here is the source or battery, and this is called the load. All right. Now, in the source, the short line is a negative and the long line is a positive. All right. And that's just how a battery is. It's got a negative side, a positive side. It'll list that on the battery if you've ever seen a battery. So in electron flow, electrons will travel from the negative terminal and try and get over to the positive terminal. The source provides them with electric potential energy, and they pass through a load. A load is anything that uses the electricity, turns it into something else. And if you're wondering, that symbol right there is called a resistor. Not that you need to know any of that for this lesson, but that's electron flow. Now, conventional current, which if you're going into college to be an electrician, is they think of it as positive charges going from the positive terminal around to the negative terminal. Other than the information you see on this slide, though, I generally think of it as electron flow because, as we know, because of structure of the atom, and electrons can be removed and moved through circuits, and protons, positive charges, cannot. So this is what's actually happening, the electron flow. But there are still when you're in a course to be an electrician, they do speak of conventional current, which is thought of as positive to negative. Really, they're the same thing. Saying negatives are going clockwise is the same as saying that positives are going counterclockwise. And the circuit symbols mean the same thing. The types of current are direct current, which both those examples I just gave are direct current circuits. That means they leave the source and come back to the source later on. I wouldn't redraw that. If we were to measure the current over time, you'd see it's a steady rate the entire time. The current only flows in one direction. As usual, pause this when you need to write something down or think about something. Things that produce direct current are batteries, and things that use direct current are anything that runs on a battery. All right, anything at all. Your phone runs on a lithium-ion battery. I don't know, just anything else that runs on a battery, guys. Anything that runs on a battery will work there. Alternating current's a little different. The symbol for an alternating source is that circle with that squiggly line there. And that squiggly line is because if we were to graph the current versus time, you'd find the current goes up and down, back to zero, right? This would be zero current, and then into the negatives. So they go back and forth, back and forth. If I were to think of one electron in this circuit, it vibrates back and forth, back and forth, back and forth, wiggles, really. And the wiggling of that electron is going to wiggle the next electron, and so on and so on and so forth. And that's what gets you this forward-backward motion of the current. In Canada, the charges change direction 60 times per second. That's referred to as 60 hertz, 60 cycles per second. Other than what you see on this slide right here, especially this graph right here, you're not going to be tested in this course on anything else involving alternating current. All of the examples from here on in are going to be direct current examples. Things that produce AC are generators. Things that use AC would be anything that you plug in. Anything you plug into the wall uses alternating current. Mathematically, current is the amount of charge passing a particular point in a circuit per time. It's the rate that charge travels through. So I stands for current. It's measured in amps, or just capital A. Q is charge, and it's measured in coulombs, capital C. It looks like a lowercase c, it's a capital C. And T, of course, is time, and it's measured in seconds. All right, so those are two new units for you, amperes and coulombs of charge. Those of you that like a triangle to help you with your algebra, I, Q, and T, just like that. The main conversion sometimes that you'll have to do would be milliamps to amps. All right, for this formula to work, you need amps, but sometimes it's helpful to have milliamps. So 1,000 milliamps is 1 amp. 250 is 0.250 amps. 1,300 milliamps is 1.3 amps. And 1.2 amps is 1,200 milliamps. That's the main conversion, amps to milliamps, and back and forth, that you have to do in electricity with current. I've never seen anybody say like a centiamp or a megaamp or a gigaamp or anything like that, but milliamps and amps all the time. All right, so the first half of your lesson here is almost finished. We're just going to do a couple of examples. That much charge passes through a wire in 1 minute to determine the current. So you just go I equals Q over T. 585 coulombs, 1 minute is 60 seconds. I don't need to see your math on that conversion, just do it. And we go 585 divided by 60, and it's 9 decimal. I'm going to round it to 1 digit, 8 amps. That easy, guys. The work today is going to be that easy, no harder than that. A lightning strike delivers a lot of charge in a short amount of time. All right, determine the current. So that's an ugly looking I. Let's back that up. I equals Q over T, 5.7 times 10 to the 7 coulombs divided by 1.5 seconds. Type that into your calculator. You go 5.7 exp7 divided by 1.5, and it gives me 3.8 times 10 to the power of 367, and that would be amps. You could also use coulombs per second as your unit, and I'd have to accept that. Last one I'm going to do with you right now is it gives you the current. A toaster draws that much current in 2.5 minutes. How much charge? So we're solving for Q now. Q is going to be equal to I times T. That just comes from the same formula. So it's 5.2 amps times, don't forget the time's got to be in seconds. 2.5 times 60 is 150 seconds. Type that into my calculator. It's 780 coulombs in 2.5 minutes. So moving right along, guys, I'm going to keep those annotations in case I want them some other day. The other topic we're going to cover today is on potential difference, also known as voltage. Okay. Named after one of the coolest names in science, Count Alessandro Volta. As electrical charges pass through a source, they gain energy. And as they pass through a load, they drop off the energy. So in a simple circuit, well, the energy is converted into a different form, and that potential energy pickup and drop off is called voltage. So you get a gain of potential energy in the source. So just picture a coulomb of charge as not an electron. It's really a group of electrons, a great big group, 6.25 times 10 to the 18 to be exact. So I'm going to call it a C for a coulomb. All right. So they gain energy in the source, and then they drop that energy at the load. And in a circuit, they just continuously go through that cycle of pick up energy, drop off energy, pick up energy, drop off energy. And they call it a voltage gain and a voltage drop. Formula V equals E over Q. The triangle for that, V, E, and Q. V stands for potential difference. And it's measured in volts, or just capital V. E, of course, is energy, and you should know that that's measured in joules. And then Q, just like with the current, is your charge. measured in coulombs, capital C. All right, so now sometimes you just say calculate the voltage, but really what they mean is calculate the potential difference, and it's measured in volts. All right, the rest of this is just some examples, guys. So we got this much energy converted into light and heat when that much charge passes through the lamp. Determine the voltage drop. Energy per charge. That's going to be 245 joules divided by 2.0 coulombs. And I'm typing that into my calculator right now. And it gives me 100, if I round it to 2 digits, 120 volts, which is your standard household voltage anyways. 1.5 volt cell can deliver 4,580 coulombs of charge before it's dead. How much energy was stored or delivered from that cell? A cell is another word for a battery or a source, okay, just in case you're wondering. So I got to think about how much energy it takes. Energy is going to be V times Q. You can jump in on the comments if I did that wrong. So that's 1.5 volts times 4580 coulombs. So I'm going 1.54580, and it gives me, I'm want to round my answer to 2 digits, so it's going to be 6,900, and that is joules of energy. So I have one assignment worksheet to go with these guys. I'm going to just go over here to Classroom before I sign off and go into your work here in classwork. So in electricity, which we're just starting today, we're finished with the energy stuff. If you haven't handed that stuff in, make sure you do. So you're going to see just one YouTube video that's going to cover both of those PowerPoints, one on current, one on potential difference. This is what I want you guys to hand in right here. And it's a Word document, probably the best and easiest way for you to submit it if you have access to a printer is just print it. And then you can submit a picture of it or submit it however you want. If you don't have access to a printer, then just answer the questions and do what you've been doing. That's just fine. I know I can see exactly. I haven't had any issues reading anybody's work in this, so that'll be just fine. And then you can consider yourself trained in calculating current and calculating voltage or electric potential. All right, guys, so that's what I want handed in for today. I got one more shorter, just kind of one more of these little lessons that I'm going to post on Thursday because it's a shorter week. And then that's going to be it for the week. We covered this in grade 9 science also, so this might be familiar to you. I hope it's a little bit familiar to you. Hopefully you have no issues. That's that thing on resistance. That's what we're going to post the next day. Next day, okay? That's all for me now. Good luck. Keep the emails and comments on Classroom coming if you guys need any help. I'm just sitting here trying to solve physics problems for people all day. All right, good luck.